Okay, well, we'll get started on lecture 5, part 1 of PIV. So we're going to go over kind of the basics and operating principles. Okay? So the goal of this lecture is to provide a background for PIV, again, which has an overview. We'll talk in this lecture a lot about the instrumentation and general approach. Tracer particles in terms of tracking and light scattering. Introduction to extensions beyond planar. This is stereo and tomographic PIV. Okay. So a bit of history, if you will. There's a long history of determining motion from change of particles in terms of debris, smoke, and photographs. This kind of can date back all the way back to early 1900s with Prandtl, who used kind of, again, metallic flakes to look at the motion behind an aerofoil. There's also, has anybody ever played poo sticks? This is, you throw you remember this from the comic, but you throw sticks into the river and you basically, you're kind of interested in them racing, but you actually can use their motion to determine how the velocity and the currents work. So, but in terms of Prandtl's, many of you may be aware that this is 80, kind of 2010-ish era, 80-year-old data ends up being analyzed by DLR with PIV. So it's kind of cool. You actually can take this really old data, that he used primarily for visualization, and actually went back and looked at these trailing edge vortices. So that was kind of interesting. Okay. So in terms of kind of the evolution is quantitative velocity data from particle streaks. You basically would put particles, illuminate them, keep a gate open on the camera for a very long time and look at the streak that's formed. Okay, this was first shown in 1930. Kind of the predecessor to PIV was something that was referred to as laser speckle velocimetry, and we'll talk about what generates a speckle pattern on an image. And really, this was attempted to use particles, but at a very high seeding density, since they ended up giving you speckle and then trying to track the evolution of these speckle patterns. In 1984, there was, maybe it's not exactly 83, 84 was kind of the first paper on PIV by Ron Adrian, which any of you that use PIV will know the name Ron Adrian. And then the first commercial system was developed by TSI in 1988. Okay, so the whole idea that this technique is based around is we're going to put tracer particles in the flow and try to determine the velocity. So what's the value of PIV? Let's go back to some of the methods we talked about in the last lecture where we have hot wire LDV. It's a single point measurement. So again, we can get a measurement at one point of the flow. If we transverse it around, we can get a field in terms of the statistics, okay, not instantaneous structure, but this is quite time consuming. You get limited spatial gradients, if any, again, maybe with the hot wire or even two LDV that are adjacent to each other. If you get two measurements close enough, you can get a spatial gradient, but it would be very limited. In terms of PIV, it's a whole field method, meaning that you get a shot at the minimum of a two-dimensional field of two velocity components and at least a few derivatives. You get instantaneous flow field and structural topology, and you get spatial gradients throughout the domain. Okay. Let's talk a little bit about the principle of the measurement and all the different components. First of all, we have to take the flow and we seed them with tracer particles. Okay, again, it is an indirect measurement. You illuminate with two successive laser pulses separated by delta t, and we'll talk about all these different components. You need a camera or a series of cameras, if you will, but you need double exposures of the particle field. Again, we get a two-dimensional displacement of the particles. So again, one laser comes in, illuminates a field, I get one image of particles. The second one comes in, I get a second image of particles. And again, every one of these components we'll go deep into. Images are analyzed over a series of grids, which are called interrogation windows. Okay. These interrogation windows need to be large enough such that there's a sufficient number of particle images, meaning particles that are transferred, images of particles, but small enough such that the velocity is uniform within the window. And there's a lot of key words in here that we're going to come back and tackle. We're going to talk about the fact that we have interrogation windows. They're fairly large, but we have to assume the velocity is uniform within the window. This is going to be one of the assumptions that we discuss in quite detail of why we have to make this assumption and what's kind of the problem with a lot of this assumption. Okay. Displacement is typically computed through cross-correlation. It doesn't have to be, but this is essentially the predominant way in which it's done now. And one thing that will set up the stage is that PIV that was developed and applied in non-reacting flows for many years before combustion systems. There's not too many things that change in reacting flows in terms of setting up an application, but there are going to be different challenges, okay, in reacting flows. Okay. So the different aspects of a system is we have a laser source, light sheet optics, camera, tracer particles, measurement settings, software, post-processing. Okay, and each one of these in this lecture, this is going to tackle, we're going to go in depth so that we can understand the different components of our measurements and the different attributes of each one. Okay, so we'll start talking first about the laser source, the optics, and the camera. So again, that's in general how a measurement works from a hardware side. Okay, and we'll tackle each component. We have a laser that fires 2 shots, and we have a camera that detects 2 images, okay? And then we're going to work on, after that, the analysis of these 2 images. So again, we need, typically the laser is a dual cavity laser, although there's nothing stops you from having 2 individual lasers that are spatially overlapped and then synchronized properly. Okay? Now, you've acquired 2 images, these particle images. This is what they look like. You've seeded your flow with part, and you acquired these images. Let's see how you get your velocity. So what we're going to do is divide the image pairs, so each image, into a series of interrogation windows. Okay? If we look at a single interrogation window across the 2 image pairs, this can be considered as a small subregion. Okay? And what we want in the small subregion is that within this, say, 32 by 32 pixel region, if you will, we have fairly uniform motion. Okay? Once we do that, we'll talk about how you actually do this, but we're going to compute the displacement of the particles. And we'll do this statistically. And once we have the displacement of the particles, we have the velocity, because we know our delta t in between the 2 images, and we repeat for each interrogation window to get the velocity field. Now again, you can already see that we get a velocity vector per interrogation window. Okay? So we already know, we talked about this yesterday, but we know that this is essentially a lower resolution measurement as compared to what the detector will allow. So let's talk about the laser. The most common laser source is the Nd:YAG. It's a solid-state laser for PIV. So we typically use the frequency double output at 532 nanometers. What you want in one of these flows is it has short duration laser pulses on the order of nanoseconds, so that it freezes the flow so that you're actually getting something that resembles an instantaneous realization of the flow. The typical operation is at 10 to 30 hertz, although in this day and age, we know that there's high-speed imaging, so we can get kilohertz rate lasers without problem. But again, your conventional system that you still operate now is about 10 to 30 pulses per second. Okay. Now, our dual cavity configuration is what's generally used. Again, I said that you can use 2 lasers. Well, when you buy a quote-unquote PIV laser, it's just a dual cavity system. A dual laser cavity system where you're generating 1 laser here and 1 laser here. They're typically combined, okay? And then you have the 2 laser beams that are spatially coincident, okay, that output. So you have 2 separate beams where their time spacing can be varied within a large range, essentially user selected, but they are on top of each other spatially. Okay? So if we think about the setup for a planar or even a stereoscopic approach, this is fairly straightforward. And we'll talk about tomographic later. The first thing we start about is, like I said, we have 2 beams. This is, again, if you have a dedicated dual cavity PIV laser, this is already satisfied. You have two spatial beams. Again, they need to be offset in time, and they need to be formed into thin laser sheets to illuminate the particles in the measurement domain. Okay? So typically, you can use, there are several combinations of lenses you can use. The easiest, the simplest to explain is a set of concave cylindrical lens and convex spherical lens. Really what happens is you have a beam. The cylindrical lens starts to expand the beam in one direction. It does not touch it in the other direction. And then when it goes through a spherical lens, it collimates the former expanding direction and focuses it into a waist. If you have it reversed, like that is shown here, this is the scenario for a diverging sheet. So again, do you want a diverging sheet or do you want a collimated sheet? If you want a collimated sheet, you typically will have the cylindrical lens first, that the beam starts to diverge only in one dimension, and then when it hits the cylindrical lens, it will collimate in the direction that was diverging and focus in your waist of your sheet. If you have the spherical lens and the cylindrical lens in this order, and depending on how you match the focal lengths, you actually get a diverging sheet that is focusing in its waist. Okay? PIV is typically insensitive to whether or not you have a slight non-uniformity in your sheet, so you can actually have kind of a diverging sheet in your field of view. And this is typically what's used for large field of view type measurements. Okay? This is kind of a overview of kind of a top view and a side view for various types of approaches. Here's the version. Let's consider we want a collimated laser sheet going through our test section. Again, we have a cylindrical lens that has some negative focal length f2. Again, and then we have a convex spherical lens that has some focal length f1. Okay? And we can separate, and we can do our geometry, use our thin lens magnification type formula. Again, and we can get our magnification, which ends up giving us our height of our laser sheet versus the original diameter is the ratio of the two focal lengths. And then we can set up this distance here in this equation here in terms of f here is negative, okay, because it's a cylindrical lens with negative concave. And so we have a negative focal length, so it also can be written in this manner. Okay? So this just gives you a way to set up your lens. For example, if you have a beam that is, say, 10 millimeters and you want a 100 millimeter sheet, the ratio and the focal lengths need to be a factor of 10. So this could be achieved with a negative 100 millimeter focal length cylindrical lens and let's say a 1 meter focal length spherical lens. Okay? Now, a couple of things you want to think about in terms of setting up a PIV experiment is if you have a thin laser sheet, clearly this gives you better spatial resolution. We know this. We'll get better spatial resolution from this because, again, all our measurements are always integrated in and out of our laser sheet. But one thing that we'll talk about in terms of PIV is that you have a higher probability of out-of-plane particle movement, right? So your movement of any flow field is three-dimensional, right? I have a laser sheet that's fixed in space. Knowing the thinner my laser sheet is, the higher number of my particles are going to move out of the laser sheet. And we'll see that this has consequence for the correlation. Now, if we have a thick laser sheet, they'll stay within there's higher probability that they'll stay in the laser sheet between the two delta T's, and therefore they're easier to correlate, but our thicker laser sheet gives us poor spatial resolution. Okay? So again, there's this balance in laser sheet thickness. Again, we'll show there's some design criteria. Depending on what your out-of-plane velocity is, we need to balance whether or not we have a super narrow to thick laser. Okay? Okay, let's look a little bit at the camera side. What do we need in a PIV camera? Okay, we already have established what we need in terms of the laser. We need to be able to record multiple images, at least 2. Thought question, what if you had a camera that gave you 3 consecutive frames? Okay. Acceleration, there you go. That's, and so that would be quite exciting. Acceleration is a very critical property in fluid mechanics, okay? So again, there is some effort. I've had some conversations with manufacturers. There is some work on essentially 3-frame cameras, although the amount of effort that goes in that may not be sufficient for production costs. So, but again, you want at least 2 consecutive frames. You really want a high dynamic range. We talked about dynamic range yesterday, and we want high spatial resolution. Really, what this means is we want a large number of small pixels. Okay. Now, the spatial resolution of modern CCD cameras is actually pretty poor compared to photographic film. Okay. So actually, when I started grad school, that's how you love stories. When I was in grad school. Actually, we had both. I'm not that old. But we had both, but people were still doing some measurements on actual film. Now, there's a pro to that, is the resolution is exceptional. The problem is the turnaround time is horrible, and the fact is there's nothing sadder than watching one of your colleagues, they take their data. First of all, you have no idea what the data looks like we do now, just in real time. You have it developed, and you get it back, and you realize it was all garbage, and you just throw it in the trash, and you start over again. So that's one of the problems with photographic film, right? So, and we also were a little bit more discerning of what we took pictures with, right? Just around the city, right? You couldn't just delete everything. You wanted to make sure it was good. So, anyway, you get higher resolution, but it's not nearly what you have in digital cameras. Of course, no one would ever want to do an experiment with film. It's a ridiculous idea now in modern CCDs. So really, you're trying to get high noise, high sensitivity. Okay, that's really what you want, even in the context of PIV images, which will show you're not really interpreting the signal as anything, but you still want low noise and high sensitivity. The reason we're going to want low noise is that we're ultimately going to do correlation between the images, and we want the correlation between the noise and the actual particles to be very low. Okay? Now, you can do single frame multi-exposure, or you can do multi-frame multi-exposure. So what I mean by single frame is you could have one frame and have two laser sheets and give it multiple exposure. And I show here just one dot, one pair of particles. Or you can have what you all use is that you have two frames, okay? The problem with the single frame multi-exposure is the ambiguity and direction. So this is really a lot of initial measurements were done when PIV was being developed in the 80s and early 90s. It used single frame multi-exposure, and instead of cross-correlation that we'll talk about, it used autocorrelation of the images, okay? And so autocorrelation with itself. And if you knew the principal flow direction, this gave you a very accurate measurement. If you didn't know, there's ambiguity in the direction. Now, one way that sort of got around this was, actually, when I was a grad student, did a lot of this, was you used two colors of lasers, okay? You had a red and a green one, and again, delayed, and then you can use a single exposure, okay? So there's no ambiguity if you separate with different wavelengths, okay? So let's look at a common method for acquiring multiple exposures on multiple frames with a single camera is referred to frame straddling. This is what you have in all your interline transfer cameras, okay? So this is kind of what the gating looks like. What we call it frame straddling is that you have two exposures. Many of you are using this. You have your interline camera. You have your, whether it's LaVision or Dantec or whatever it is, or your PCO cameras, whatever you have. You have cameras that interline transfer, and they look like this. They basically have a short exposure and a long exposure, and you essentially straddle these two exposures between your two pulses, okay? And these obviously can be changed based on what the user wants, what your flow settings are, okay? Now, what we typically have, you have this first exposure that's very short, anywhere between half a microsecond to 200 microseconds, and then you're left with this very long second exposure. This is difficulty that everyone has. You always look at your two images, and if you haven't done any filtering or anything, optical filtering, you have one that looks like just particles, then you have one that has all that nasty background in it, okay? That's due to the long exposure. And so what you have to ask yourself is, why so long? And the second question is, where can this be a problem? Well, the second one can be answered first is in very highly luminous environments, okay? So just regular flames itself are enough luminosity at times. We took some measurements recently, just actually a few weeks ago, just in turbulent lean premix flames. That's not considered a very luminous environment, but the background signal was still high enough to it was about 1/2 of the particle signal, okay? Because the student unfortunately just forgot to put the optical filter on, but anyway, we can redo the data. But anyway, it's just amazing how much the signal can be. Now, if you go into non-premixed flames or sooting flames, these are intractable issues, okay? Or if you have significant surface issues, you can actually have a problem. So why is it so long? So let's talk about a simple interline transfer camera. Let's say we have a 1 megapixel camera. There's our pixel, and next to it we have a frame storage area. Okay, if you think about general architecture for CCD, there's going to be the active component, and then usually there's an area, a buffer next to it. Okay, and so what happens is it's all about transfer time, right? I have only in an interline camera or PIV camera, I only have one sensor, right? And so the first illumination comes in, illuminates my particle field, it comes in, that pixel reads out the charge, okay? I have to do something with it. I have to get rid of it, or that pixel is no longer can be used. So I can very quickly, if you will, I can dump it to a neighbor, I can store it over there, and that takes somewhere on the order about half a microsecond or a little bit longer depending on the camera. But then once I do that, the camera's ready to go again, or that active element's ready to go again. But then after I take the second one, since I've used up all my storage, I have to get rid of it, so I have to read out the information on the camera, okay? And again, as I'm reading it out, the circuit, the sensor is active while I'm reading it out. So this is actually the readout time. Again, you can call it to the PC, okay? So you have a very quick transfer time to a neighboring storage site. You have a very long readout time. And this creates, again, quite a problem in very luminous environments, or it can create a problem. Okay, now let's start getting into some of the details of PIV and really some of the assumptions that are embedded in here. This is a very nice, I love this figure because it tells you all the things that could potentially go wrong without going, I don't have to even talk anymore, we can look at, well, not all things, nothing on the processing, but on the fluid mechanics side, this tells you a lot about the measurement. Okay, so let's assume here we have a particle, just a single particle at time 1, and we have that same particle at time 2, okay? Let's assume what we have here is what the true fluid path line was. Okay, and for whatever reason, we put in a particle that just doesn't quite follow the fluid mechanics. No one told that particle it has to follow the fluid, right? It's going to be subject to its own drag, which we'll go over in a little bit. So let's say it has its own particle trajectory. That's just slightly different than the fluid line. Okay, so the first thing that we'll look at is that the velocity at this point in time actually would be drawing the vector tangent to this particle. Okay, and so if we do that, if we draw a tangent to that particle, we end up with what we would call VI, okay? Okay, that's the actual, that's going to be, let's see, we're going to have, VI is going to be the particle velocity. If we draw a tangent to the actual fluid path line at that time, that's the actual velocity, okay? So the two have even at this point, at this particle, the particle velocity and the true fluid velocity are different. Okay? Now, the way that PIV works, forget about the correlation yet. We've allowed this evolve somewhere, okay? And if you think about it, we don't even have to talk about this in detail. The underlying assumption is that that velocity is linear between the two time frames. So we draw a linear line here, and that's our velocity if we do everything right. And again, we're not going to do everything right. That's everything right. That's the velocity from PIV, okay? So, and then at this particle where we say, okay, this is the velocity, the actual real fluid velocity may actually be that, okay? Or the particle velocity may even be tangent to that. So what we have here is that we'll start with, for optically homogeneous fluid, okay, we already know this, motion can't be observed. So again, we're adding tracers to the fluid. They serve as scattering sites for the laser light. And the fluid motion is represented as the particle displacement. Really, again, what we do is we're saying the gas motion is somehow directly related to these tracer. And we assume that the tracer is a direct representation. It faithfully follows the flow, and that the way that we analyze the flow faithfully gives us the velocity. But we can already see here that there can be multiple problems. Not only do the particles do not have to track the fluid, but the way that we interpret a velocity vector between two times does not necessarily have to be what the fluid velocity is. Okay? So again, there's always error between the actual fluid velocity and the inferred velocity from particle displacement. Okay? Now, let's talk about a bit of what we have to assume about the tracer particles in PIV. What do we assume? We assume particles follow the motion, and they also don't alter the fluid motion. This is reasonable for very small particles. This is not reasonable as the particles become larger. You end up, again, you can think about in sprays and particle-laden flows, is you end up with something called two-way coupling, where the particles actually influence the turbulence. Okay? They can attenuate, they can modulate the turbulence, they can enhance it or they can attenuate depending on their size. What we generally assume in PIV is, though, that the particles that we put in passively follow the fluid motion. Okay? We assume that the tracers are distributed homogeneously. Okay? Now, I don't know about you, but that's an extremely difficult thing to do, right? You run flow through a seeder and then it goes out into your flow in your combustor. It's very difficult for you to have a perfectly homogeneous distribution of particles. Okay? The reason you need to do that is, again, when we go into analysis, this is absolutely needed to obtain an unbiased estimate of the displacement field. If you have a preferential direction or seeding, the correlation will be biased in this direction, okay, when we start talking about the processing. So you need your tracers as distributed as homogeneously as possible. So since we can't really tell how we're doing this, we make the assumption that there's homogeneous distribution. And again, uniform displacement within interrogation window. So why do we assume a uniform displacement? Okay, so let's come back to this. And we haven't even talked about the correlation process yet, but again, we know we put these tracers in, we have these two images, and I'll go into detail very shortly of why we can't just track the individual particle motions, why we have to do correlation, why we have to do statistical correlation. But then why do we have to assume that we get this uniform motion within the displacement? So let's talk about physical first. Since you already know from yesterday, we get the velocity vector from correlating two interrogation windows. If we have non-uniform displacement within the windows, then we have internal gradients. Okay? If we have gradients within the flow, that means the derived velocity would not be characteristic of all or any of the velocity inside the interrogation window. So if we allow ourselves to believe that there's non-uniform displacement, then the very concept of getting a single vector for the correlation for the window makes no sense. It's actually an ill-posed question if we allow there to be internal gradients, okay? Because we don't know what that vector means. But now in the processing, there's an important part. We will know, like you said, all of you, or not all of you, many of you use PIV, and those of you who use it know that, again, I've said this over and over, we're going to get the displacement using spatial correlation. Well, we have to think about, it actually ends up using cross-correlation, right? But spatial correlation, the cross-correlation to windows, is actually only an estimate of what's referred to statistically as the two-point ensemble correlation. They're identical for statistically stationary ergodic process, okay? So this essentially spatial correlation we're doing to the windows, the cross-correlation, is actually only accurate or appropriate, is the better way to say it, under the case where we have uniform displacement. Really, to look at two fields that have moved, we need to do a two-point ensemble correlation. But that analysis is quite difficult, and cross-correlation can be done via FFT. It's very simple. And therefore, if we have a uniform flow, then the cross-correlation analysis is reasonable. Okay? So really what happens if we don't assume that we have uniform displacement, a lot of things that we just do in the processing breaks down and become ill-posed. Okay, let's go back to our particles now. What about, now we need to start, one of the tougher things to deal with is actually selecting suitable particles and making sure they track the flow. Really what we need is a tracer that's small enough to follow flow. We know this, right? You can't put a bowling ball in the flow. It's not going to go anywhere. You can't put a marble. It's not going to go. So your tracer should be small enough to follow the flow. But the smaller they become, they don't scatter light. Light scattering basically goes as the diameter of the particle to some size. And we'll show this in a minute. So they need to effectively scatter light so you can collect them, collect the light, but we need them to be small enough to follow the flow. So the tracing ability, or the tracking ability, if you will, and the dispersion of particles depends on the aerodynamic characteristics of the particles and the fluid that it's put into, okay? The visibility, or the light scattering properties, will actually depend on the geometry. So the visibility depends on the scattering characteristics, and the scattering characteristics depends on the size as well. So there's a trade-off, right? The larger particles they are, the more light you get. The smaller the particles they are, the better they follow the flow. So we have to find a nice medium between there. And we'll go over some of the analysis. Is that it's a very sensitive parameter for properly tracking the flow, and typically in reacting flows in combustion, we'll need to use particles that don't melt. So we use ceramics, and ceramics tend to clump, and they become very large particles, and they have very poor tracking characteristics, or they can. Okay, so let's look at the light scattering. Light scattering is characterized by the cross-section C. And so really, this cross-section is just a ratio of the total scattered power to the incident intensities. So you send in a certain amount of light, and a certain amount gets scattered off, and this is essentially a scattering cross-section. Okay? Here's a graph that shows for refractive index of 1.6. Here's our scattering cross-section, and here's a particle size normalized by the wavelength. So you can think about if we have kind of a 532 nanometer laser light, 1 is a half a micron particle. Okay? So if we look at some scattering cross-sections just roughly, if we say the molecule, this is kind of how, if we have a molecule on the order side molecule, the scattering cross-section would scale actually as the wavelength, as the particle diameter to the 6th power, okay? And this kind of shows you kind of a cross-section. If we move to a 1 micron particle, we kind of in this regime where things scale to the 4th power. We may have something that's around 10 to the minus 12. And then as we just 1 order of magnitude, 10 microns, we may scale as d squared. But as you can see, this incredible sensitivity if we go back to very small particles. This is why this is the Rayleigh regime. But there's a significant difference in signal by just changing the particle by just a factor of 2 or 3. Once you get out into this region, there's much less sensitivity. Okay. The particle scattering is typically described by Lorentz-Mees solution. We assume that these particles are spherical, and so we call that's why we refer to it as Mees scattering. What happens is, again, just more broadly, Mees scattering is used to describe the situation where the particles is on the size of the wavelength. If the diameter of the particle is at least an order of magnitude less than the wavelength, this is really the Rayleigh regime. And this is where essentially small particle scattering, or Rayleigh scattering approximation is valid. So the particles that we typically use, again, and our flows are on the order of the wavelength, especially after they clump. Even if you start off with really small particles, even 50 nanometers, they're a half a micron by the time you're imaging them. So here's kind of scattering, polar diagrams of the scattering, light scattering by an oil particle in air, and you can see the differences. If you look at each one of these contours represent sort of 2 orders of magnitude in intensity. So this is a 1 micron diameter, this is a 10 micron. You can just count the rings and get how many you have, 10, 3, 5, 7, and those are shoved in here. So you can actually see way more intensity, of course, as you would imagine for a 10 micron. But you actually can also start seeing kind of the geometric solution. If you go down even smaller, you get something that generates sort of spherically and in all directions equally. But now as these particles start to become larger, these ones that we tend to use for PIV, where do we go? We end up having a preferential direction, okay? And again, well, we'll come back to this, but again, this direction is called forward scattering. Backward scattering, and then most of our imaging is done at 90 degrees. Okay. So tracer particles, again, turn out to be a critical consideration both for LDV and PIV. Okay? And so really, again, I want to emphasize that there's this compromise between flow tracking and scattering efficiency. Again, our tracking is going to depend on particle shape. When we assume it to be spherical, then the geometry really reduces just to the particle diameter. The particle density, again, you know, is it a metal, is it a ceramic, is it a liquid? What is it made of? The fluid density, are we in air, are we in water? And then the viscosity of the fluid. Okay? So let's start looking a bit at particle tracking. And let's look at essentially the response of a single particle. And the way we do this is we start with Newton's law of F equals ma. Okay? So we're going to look at the mass of the particle, the acceleration of the particle, and all of the forces acting on the particle. Okay? So what we can do here is the mass can just simply be the density times the volume, and we're assuming it's a sphere, and the acceleration is the time rate of change of the velocity of the particle. And this needs to be equal to all of the forces acting on the particle. Okay? We also are going to need to define the fluid mass that's occupied by a single particle. Okay? And this is important, something called a resistance force. But we have the mass of the fluid is going to be the density of the fluid, but then it's the volume of the particle. Because as a particle sits there, it's displaced the fluid out of that position. Okay, so let's lump in all of our forces experienced by the particle. Okay, so the left-hand side, we already know that's just the acceleration, m times a, right? So we have mass times acceleration, and these are all our forces. Okay, we have viscous drag, according to Stokes' law. Okay. We have the resistance of an inviscid fluid to the acceleration of the sphere. This comes from potential flow theory, sometimes referred to added mass. Again, this is when, if you want to start moving the particle, the fluid actually resists that initial acceleration, and there's a force applied there. We have acceleration of any particle leads to a pressure gradient in the vicinity of the particle, and so this is the force of the pressure gradient. And then the density of the fluid and the density of the particle are not the same, so we can have buoyancy effects. Okay. What we've left out of this is stuff that you do have to consider in high-speed flows. You know, we have nonlinear drag, we have Basset history effects, which we have unsteadiness effects. So we've left off a few more high-order terms already. Okay? So if any of you have worked in high-speed flows and you've done this type of analysis, you leave a few more terms on here. Okay? Now, let's get rid of these terms. So if we have small particle Reynolds number, where the Reynolds number is less than 1, you'll call this from undergrad, this is Stokes flow, we can get rid of all of these. Okay, they turn out not to be important. Okay, and we could show that, but that's not very interesting. So let's see what constitutes a small Reynolds number. Okay, so our Reynolds number again needs to divide as velocity times a length scale over a kinematic viscosity. So our length scale here is the particle diameter. So let's say we take a 1 micron particle, it's in air. It's moving at 10 meters a second. If you do that, the Reynolds number is 0.67. Reynolds number less than 1, Stokes will apply. But looking at this, you're probably thinking to yourself, okay, that's a 1 micron particle moving at 10. What if I'm moving 100 meters a second? I'm already at Reynolds number 6 to 7. That's not really Stokes flow, which really sometimes is represented as much, much less than 1. Well, what you do is that even if the Reynolds number based on the particle diameter is greater than 1, we can still assume Stokes linear drag. These things start to become increasingly more important, but they still are not nearly as important as the Stokes drag. And for analysis, it's usually reasonable to just assume that's the viscous drag is the only component. Okay? This gives a conservative estimate. Actual drag tends to be higher. So let's work only with our viscous drag, because what we're trying to do here is find a characteristic time of the particle. If we can find a characteristic time of the particle, we can say, how does this respond to our fluid mechanics? Okay? So let's define Vp as the magnitude of vector Vp, and capital U as the magnitude of vector U. Okay? So these are just the scalar magnitudes. What we want to ask ourselves is that if we have a step change in velocity, let's say the velocity of the fluid changes just like that, we have this instantaneous change, how quickly would the particle respond to that step change in velocity? Okay? So again, let's divide through by the particle mass. We can then go substitute back in the definition for based on volume and density, and you end up in one dimension. We'll just consider the scalar components u and vp just in one dimension. Okay? We can rewrite this as the time rate of change of the particle velocity is 1 over a characteristic particle time, just defined in this manner, times essentially a slip velocity, or a slip, the difference between the particle velocity and u. Okay? So let's integrate. Okay, we integrate this equation, we end up with this expression. And let's add some initial conditions we know. And then what we do is we find that the particle velocity, the ratio between the particle velocity and an instantaneous value of u can be written in this manner, where you can see that the difference between the particle velocity and the actual fluid velocity is just represented by this characteristic particle time. Okay? And the particle time was a function of the fluid parameters, the particle parameters, and the particle size mainly. Okay? So really, now for this to have any meaning, we have to evaluate this particle response time against a relative fluid mechanic time scale. It doesn't make any sense by itself. Okay? So the Stokes number is what's usually used to define how well a particle responds to fluid mechanics. The Stokes number is the ratio of the particle response time to a characteristic fluid mechanic time. So we have our particle time scale and we have our fluid mechanic time scale. Okay? So really the Stokes number determines the degree of coupling between the particle and fluid. So let's look at some limits. If Stokes number goes to 0, the particles actually behave like perfect tracers. They're like massless tracers. Like it's like a massless Lagrangian tracer in a computation. Okay, that's what we want. We want Stokes number to go to 0. If they go to infinity, they are completely unresponsive to the flow. Okay. A common value of the fluid mechanic time is the Kolmogorov time scale, which we'll assume this is we talked about yesterday in the little bit on turbulence background. This is the turnover time for a smallest eddy. Okay? So you want to, in some ways, kind of initial analysis is to evaluate your characteristic particle time to the Kolmogorov time scale, which was defined in the last lecture. And we really say, okay, what if that Stokes number is small? Well, a good criteria is that the particle time is about 1/10 of the fluid mechanic time scale. If this exists, then we generally say that the particle sufficiently tracks the fluid mechanics. Surprisingly, this is not satisfied very often, and I'll show you a different analysis which shows that, generally a lot of the particles that we use both in turbulent flows and reacting flows do not follow the flows nearly as well as we think they do. Okay? So there is an alternative method by Melling, which I like. Equation 61 can just be recast in this manner. Okay? All I've done is substituted out some things, and C is the characteristic frequency. All it is 1 over the particle time scale. But what it actually did, and I encourage you to go look at the paper, it's in Measurement Science and Technology, is that under the conditions of homogeneous stationary turbulence and using measured energy spectrum for fully developed pipe flow, you can actually end up with this expression. And instead of worrying about the analysis getting there, let's actually look at what this expression says. It's the ratio of the particle squared over the fluid squared. So we have the velocity of the particle squared over the fluid velocity squared is inversely proportional essentially to this characteristic frequency, okay, omega c. And omega c is the angular frequency of the turbulence, and Fc is the turbulence frequency. This is the frequency of interest. This is how well we can follow it in terms of hertz, and this is the angular frequency, okay? And so if you go and look, we have to choose an acceptable criterion. And so what Melling proposed was that if the particle, this squared, is about 0.95, and if you go and take the square root of those, this actually becomes like 0.8. So really what you're saying is, like the particle velocity is following the fluid velocity to some criteria of about 0.98. Then the response to the particle of any size can be determined. So let's say we use this criteria. So I mark this here, okay? Well, let's try to interpret this chart. if you look at what's on this chart before we go on, you have this kind of ratio UP squared over UF squared, and let's say we need everything to fall above 0.95, right? That's where we're saying marked. What are these? There's these curves that are essentially this constant c. Well, all of these are, remember, this is just the inverse of the particle time scale, okay? So again, that's all these curves have been, that last solution from the previous page has just been plotted out everywhere. That's all this is. Now, let's take a 1 micron glass bead in air. And that's not that off of what you would use. Let's say, glass, you would use a ceramics close to glass. Maybe you have 1 micron bead. Again, if you go through and put all your numbers in, you end up finding that your characteristic frequency is 1130 hertz, right? Okay. So what that means is that this particle can effectively follow a fluid timescale of about a millisecond. That doesn't seem that great. This is a micron glass bead, micron particle. Many of you have been operating with micron-sized particles, and therefore you're only effectively following timescales of about a millisecond. Okay? Now, if you can move down to half a micron, you can effectively follow fluid scales of about 100 microseconds. So you can see there's a substantial sensitivity to the D. Now, the reason why I brought up a micron and a half micron, again, half micron is a pretty nominal size that people use. But again, when you have ceramics that you'll have in reacting flows, these particles cluster together, right? You end up with much larger particles. And so these larger particles cannot effectively follow the smallest length scale. The smallest time scales, okay? And so depending on which criteria you use, whether you use analysis like this or use kind of a Stokes analysis, you also can get different answers. Okay? So it's important to look at the characteristics of your particles. Like I said, in general, a lot of the particles that we use do not properly track the flows, or at least the smallest timescales, the smallest fluctuations. So when I say 1 millisecond, that means it can properly follow anything that's moving in a characteristic period of about 1 millisecond. But turbulent length scales that are acting on smaller time scales, it's effectively like a low-pass filter. It's not following these fluctuations, okay? And so again, the consequences are, it just depends on what you're looking at, okay? So if you're only looking at large-scale dynamics, this may not be a problem. If you're actually trying to look at some small-scale processes and some instantaneous interactions, you may not be looking at quite the right process. Okay, let's look a little bit at dimensionality. Okay, it comes from Scarano, and it's 2013. This kind of tells you kind of what's out there available today. We have this time bracket, and we have these space, and we have all these velocity components. You can start down the way that this works. You can start LDV, right, which can give you a single component, and again, it may be able to give you time. Probably should build a little bracket on that. But then you can move to 3 components. Oh no, they are in time. I'm at a bad angle. These are down here. So you get a single component in time, 2 components, 3 components in time, right? Then we can work on regular PIV, where you get X and Y. You get X and Y. You get 2 components of your velocity, and you get them in 2 components of space. And you can just build on into where we move all the way up to high-speed tomographic PIV, where you get all 3 components of velocity in all space and time. Okay, so there's a hierarchy of techniques to use, moving all the way from single point all the way to, say, 4D measurement. Okay, so let's talk about what you get. Traditional planar PIV is often referred to as 2-dimensional, 2-component. You get 2 components U and V, right? So you get 2 of 3 components. You get only 4 of 9 components of the velocity gradient tensor, only 4 of 9 components of the strain rate tensor, and only 1 of 3 components of the vorticity vector. Okay? Now let's work really hard. We add another camera, and we do stereoscopic PIV. And we'll talk about this, we use 2 cameras arranged in a stereo configuration, and we're really excited. We measure all 3 components of the velocity, but we've only added 1 additional component of the velocity gradient tensor, no additional components of the strain rate tensor, and no additional components of the vorticity vector. Now, if we go to tomographic PIV, we use 3 or more cameras, measure typically 4 to measure velocity and a volume, and we get everything, okay? So there's a substantial jump going from stereo to tomographic. There's also a substantial jump in effort, and we'll talk about this. Stereoscopic is a straightforward extension from traditional planar PIV. Now, you can also play some other games that if planar and stereoscopic PIV are performed at high sampling rates, depending on how you orientate the laser, you can actually use Taylor's hypothesis to get additional terms. And I put with the normal caveats for Taylor's hypothesis. So you can think about this if you slice your laser such that, let's call X, as we have X, Y, and Z into the board. If we put our laser in the YZ plane, such that in this configuration we would be directly measuring, the V and W components, right? You can actually, you'll measure W in time, and with the mean convective velocity of U, if you know that, you can actually end up backing out gradients that you don't have. So you can orient this in a few different ways. You actually can get some, you can end up getting quantities that you don't have. Like you don't have, with a laser sheet like this, you don't have the W component in the X direction spatially, but by measuring the temporal derivative and applying Taylor's hypothesis, you can derive it. And so this is lots of time what's used, especially in a stereo configuration. You'll have a time-resolved stereo configuration where you'll apply Taylor's hypothesis to get the components of the velocity gradient tensor that you don't have. Okay. Stereoscopic PIV, again, we know uses 2 cameras in a laser sheet. So we haven't done anything like Tomo. We haven't spread anything out into a sheet, laser slab. We still send a sheet through, and we have 2 views. So it's the same way that we work. We work in stereo vision. We have camera 1 and camera 2. We refer to it as I1 and I2. And we have sensor 1, which is brain, okay? And we have some really cool optics, and we have really good data processing in between. So we use stereo vision in the same way. And what happens here is that you end up, you record 2 distinct views. You have one that has a perspective from the left and a perspective from the right, okay? And then we'll talk about this in the next lecture of how you actually analyze this. But what you have up with 2 images, and you end up converting those to one single planar, and you get the out-of-plane component. But one thing that has to be satisfied is what's called the Scheimpflug condition, which means that the lens plane, okay, the lens plane, let me find the lens plane, we have the image plane and the object plane all have to come. We have the image plane, the lens plane, and the object plane all have to intersect at a common point. If we do that, then this entire field of view is in focus. Otherwise, we have portions that are out of focus. So the Scheimpflug condition must be satisfied. And again, any type of commercial system would be, your cameras would be set up with Scheimpflug adapters to make sure that this intersecting point is satisfied. But we'll talk about this, again, how you do the analysis. And then finally, tomographic PIV was first introduced in 2005 by Elsinga. This is Fabio Scarano's group. And what you do is you expand the laser into a slab, a thick laser sheet, so that you're actually looking at a volume in space. Okay? You need to use, again, 3 or 4 cameras, 3 or more. The more cameras, the better. Okay? You have these multiple distinct off-axis views. Okay? Every camera has to have the Scheimpflug condition, the same as stereo. What you have to do before you can even do any type of analysis is you actually, remember stereo, we're still looking at planar image, 2 planar images. But for tomographic, you have to do 3-dimensional volumetric reconstruction of the particle fields. And so there's many algorithms that handle this. This is done through different, where they're MART-type algorithms, multiplicative algebraic reconstruction, tomography, things that were adapted from, the medical industry, CAT scans. And so the more views, the better, really better in terms of the particle volumetric reconstruction. That's a significant part of this technique. Once you have the volumetric volumes, then you perform volume cross-correlation to get your vector field. And so we'll talk about some of the details in the next lecture. All right, and 409, questions. Again, What we spent the most time on this lecture was talking about really particle characteristics. So we talked a lot about the hardware, the ins and outs of some of the equipment that maybe you haven't considered. And really one of the big keys we talked about are the particle tracking characteristics for PIV. Okay? Question? Yes? So you were talking about thermophoresis is really a heat problem. Yes, thermophoresis turns out, I'll talk about that a little bit in the next lecture. Thermophoresis turns out not to be a major effect unless your particles get really small. I mean, they have to be really small. So anything that we normally look at, the air is on the order, a kind of a meter a second. So it's not a very long. So there's many people who will write paper who will say that's a big deal, but it really is only if you have, so if you're using like 10 nanometer particle for some reason, thermophoresis it can be a big problem, but for our general particles, they're not as significant. Yes.
So for standard PIV, you're usually working with a relatively thin laser direction. And if you're working in reacting environments, you're going to have very strong temperature gradients and thus density gradients.
Yes.
Something that is considered, and how much of an effect does that have?
All right, so beam steering is affecting all diagnostics and reacting flows. The beam steering from shot to shot, you can conceivably, because you allow the particles, we'll do this over kind of the design rules in the next lecture, but you allow the particles to move a substantial amount, so there is a true fluid mechanic time between the two shots, so the flow field can move, and therefore your two beams can be coming in at two different locations, okay? And so this is a source of uncertainty. It's not usually taking into account any type of uncertainty, but beam steering, of course, and if your beam moves, even if your particles for some reason move, you would see a different set of particles, and therefore there would be uncertainty in your correlation. But yes, beam steering affects all measurements, and the more precise that you need alignment, the more difficult this is.
Okay.
There's.
I was just curious, do you typically
Oh, well, if you're talking about because the change in density, because you have reacting flows. So yeah, in the next I'll show, this is one of the challenges of actually getting good seeding. Maybe I'm not, hopefully I'm answering your question, because cold, when you have the density effect, the divergence, when you're hot, you're left with a lot less seed. And so that's one problem in seeding, but you're talking about in terms of just a correlation?
Yes, so like you might have like
Oh, so you're asking a different question. Okay. Let me make sure I understand. So you have a certain amount of flow rate, and then you've added mass.
yes.
Generally, the mass of the particles is assumed to be negligible.
Okay, and even if you
Yeah, I mean, if you sum them up, again, if they're tracers, their mass has got to be pretty small, right? Because if you start getting stuff that has an actual appreciable mass, then they're not going to be very good flow trackers. So in that limit, kind of satisfying that they're good flow tracers, they have a pretty small mass. Okay. There was anybody else? Okay, well, let's take another break, and we'll resume at 4:30.